Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series.
It's my pleasure today to introduce our speaker, Babak Shahbaba. Dr. Shahbaba is joining us from UC Irvine, where he is a professor of statistics with a joint appointment in computer science. He's a Chancellor's Fellow. This is a distinction awarded to those who have been identified for extraordinary promise for world-class contributions to knowledge. His research focuses on Bayesian methods and their application in data-intensive biomedical problems. He has worked on a wide range of applied and collaborative projects applying statistical methods in the areas of neuroscience, genomics, and health sciences. Additionally, he works on the development of efficient sampling algorithms. Currently, he is a PI for 2 NSF-funded grants, as well as a grant from NIH. So, Babak, thank you for joining us, and go ahead and get started when you're ready.
Yeah, thank you so much for the invitation and the nice introduction. I'm very happy to be here today. I have been at Lawrence Livermore National Lab before pandemic, and I have talked to Mike several times, and looking forward to collaborating with you guys because, as I mentioned to Sarah earlier, that we are building a data science institute here at UCI, which makes us, it's a natural collaboration with the data science institute you have there. Today's talk is more about the research that we have been working on over the past few years. It's about data-driven mechanistic models. It has multiple design and inference. These are the main papers that this talk is based on. There are 2 different papers. I will start with an illustrative example. I usually don't do this, but there was a suggestion that maybe for some people who are not familiar with this, maybe an illustrative example like a tutorial might be a good starting point. So I will start from there, but then I will move on to the actual real biological problem that motivated this research. And after that, we present the specific model that we developed to study this biological system. And I show how our model can be used to design experiments that involve mechanistic modeling. This is not very common. And to the best of our knowledge, this approach is like one of the first few attempts at this. And then towards the end, this is the inference part and the computational part. I will talk a little more about the computational challenges and actually implementation of these models at the end. But to start, this is one of my former PhD students recently developed a course on this Bayesian mechanistic modeling, and I will show you the GitHub page later on if you want to go and read more about it. But I just used one of the example that he used in his class, which was like a logistic growth model. This is a simple model for population growth with limited resources, so it can't grow forever. So there, at some point, the rate of growth goes to zero. And so this is a model people have been using for basically how this population size changes over time. It's a simple model, and R is defined as the growth rate, and K is the carrying capacity, basically shows that how far the population can grow. The nice thing about it, this has an analytical solution. Everything else, I'll talk later, they don't have an analytical solution, but this is a nice illustrative example where you can see that there is an analytical solution to find the population over time. So now, how can we put this in a statistical framework? The simplest way to do this, you basically assume that the mechanistic model, the one that I just showed you earlier, basically defines the mean model, and the actual observed data that you get, it basically is a noisy version of this model. So you have the mechanistic model here, and then if you add some noise to it, that's the actual observed data. So this allows to account for the uncertainty and the randomness around the model. And if, of course, if you do this, then you can, like assume some distribution for the noise. Let's say Gaussian. It's not always a best choice, but it's a convenient choice. When you make that assumption, then you have a statistical model, a probabilistic model, which from there you can get the likelihood function, and you can continue like as if you do, like any other statistical model, except that the mean here comes from a ODE or PDE according to some mechanistic models. But everything else now from here on, it looks like just a simple model. So this is just an illustration. So we simulated some data, and we assumed some prior distribution on model parameters, R, K, and sigma. Sigma is the variance of the noise, and R and K I mentioned earlier. And then using a stand, you can just run the model and get the posterior distribution on the model parameter and fit the model. And this is a 95% credible interval. And this is the median. And you can see it recovers the underlying model very well. Of course, this is a very simple model. So this hopefully just shows how we connect the mechanistic models to data and perform a statistical inference. So if you are interested, you can go to this, my student, this is the course that he designed, and we actually, the data DSI here, we offer courses. So this course was offered through DSI here at UCI. And if you want to go, I think I have so the GitHub page, if you go there, it has this example with this, how to simulate the data, the stand codes, how to run the codes. So for, I don't know if there are students in the audience or if there's someone is interested. So you can actually go and look at this example from the GitHub page. Luis Martinez Romelian was my former PhD student. You can find his GitHub page and read this tutorial. And there are more tutorials, there are more examples here, like in his GitHub page for this course, so you can find those. Let's go back to the talk. So this was just basically a simple example to show that how these models works. Of course, we were working on some more complex problem was in collaboration with scientists here at the School of Medicine. We have been investigating hematopoiesis. So you might know about this, but if you don't, like, this is just a very brief introduction to hematopoiesis, which is a very complex and highly regulated system that produces billions of mature blood cells. It starts basically from these hematopoietic stem cells, which call them HSC, and they basically produce these multipotent progenitors, MPP, and then they continue through the like this process. They eventually lead to more mature blood cells at the end of this hierarchy. It's a very complex problem. It has to be tightly regulated to make sure there's an appropriate proportion of HSC and MPP in mature cells. So it's a very complex and highly regulated mechanism. And our goal was to understand the underlying mechanism of this process. Of course, we want to just to understand the normal process. That's what we're going to focus on right now. But of course, later on, you can see what happens when something goes wrong, and it leads to various diseases. But at this point, we just wanted to understand just a normal process. So our goal was, our specific goal was that we wanted to basically develop a statistical framework for analyzing such data collected from the hematopoiesis process. And also design an experiment for follow-up experiments that we wanted to do. This is not, as I said, this is not commonly done. Usually they just go based on some assumption. We need like 4 rats, and we are going to observe them, over 5 time points. There is no, most cases, there is no clear way of how you design such an experiment. And as I said, like later on, we wanted to make sure this is easily implementable through, like developing computational methods. The specific data we collected was through a perturbation experiment where animal subjects were exposed to some external agent. In this case, was a low-dose radiation, and that disturbs the system, but the system responds and evolves and come back to its normal status, and we wanted to basically monitor that process. For simplicity, at this point, we just focus on HSC and MPP. So basically the first part of that hierarchy that I showed you. So we didn't basically observe the whole process up to the mature blood cells. We just focus at the beginning, at the root of that hierarchy. And as I said, the perturbation was through subjecting animals to low-dose radiation and basically measured the number of HSC and MPP using flow cytometry. So this is basically the data that we observed. This is for HSC control without radiation, HSC with radiation. As you can see that it drops, the number drops after radiation, the number of stem cells dropped. And then it seems that it's coming back. And then for MPP, similar things happen, like these are MPP under control with no radiation, and these are MPP with radiation. So one problem that this is not very different than many statistical problems that you might have seen in other contexts. These are not true time series, even though it seems that we have these observations at time 0, day 1, 2, 3, 4, 5, 6. These are not true time series. I cannot connect these points because every time they measure, these are from different animals. So this is one mouse, this is another mouse, this is another mouse. So these are different mice. So these are different subjects. So they are not the same subjects. We don't have similar, we don't have the true time series that we can model these things over time. So that creates some challenging. So how we did that. So this is, now I'm going to talk about this specific model that we developed for this. This is just our estimate of HSC at time 0. We basically put some priors, and then we get the posterior with radiation, posterior with control. This is how our estimates looks like at the baseline. But if this is just, we want to just look at the distribution at the baseline, but we want to model the dynamic system. We want to model how this process evolves. So we have an underlying model for how the number of HSCs and MPPs change over time, respectively. These are usually, as I said, they are done, they're developed through some mechanistic models. In this case, an ODE model that models the number of HSCs and MPPs based on cell cycle progression and replication parameters. So the model, it's simple. It's not. It was developed before. Basically, it shows that how HSC changes over time and how MPP changes over time, depending on some parameters. Eta basically quantifies how rapidly cell divides, and P basically quantifies the self-renewal rate. This was developed earlier by Lander et al. In 2009. And but that's not just that simple. There are some regulation system in place through these gamma parameters. So there is a feedback regulation that they're subject to. The actual model that we ended up using, this is where we started. We actually made some changes. The actual model is a little more complex with feedback and feed-forward parameters. But I'm not going to go into too much details on that. As I said, at the end of the day, we have this mechanistic model that just shows that how these HSC and MPP changes over time. And now, as I said, the problem was that this is not a true time series. So we wanted to develop a statistical framework that connects the mechanistic model that defines how the number of the cells change over time to the actual data that we have observed. So the way we assumed, very similar to the example that, the illustrative example that I had earlier, we basically assume that there is this mechanistic model basically defines some trajectory, some latent trajectory, because we didn't observe it directly. So it assumes some latent trajectory, which is, again, like you can assume that that's the mean model, and then we put some noise around it to account for uncertainty and the actual noisiness of the data. So the ODE model basically defined that, the latent trajectory, and the actual observed data, of course, depends on that trajectory, and along with some additional sources of variability, some noises, which in this case, we assume that there's some technical noises and some biological variances that these animals, just at the beginning, they're just different. So their cell counts, they're at different levels. So we account for that. And we account that there's, like there's some technical variability as you measure these things. There is some variation, which we show with sigma t. So at time t0, we assume that we assume a log normal model. So there is that mean model, the trajectory that it comes from the mechanistic model, plus some technical variation and some biological variation. And then at time t, as we continue, then we already accounted for the biological variation at the baseline, and then everything else beyond that, we just assume that it's just a technical variance. But again, like this comes from the mechanistic model that we discussed. So the mechanistic model basically defines the mean at the time 0 and over time. And then we basically add some variance to it, some noise to it, and that would be basically defines the distribution of the observed data. Very similar to the simple illustrative model that I discussed earlier, except that, of course, this mechanistic model here is a little more complicated than the one that I showed earlier. So we collected n samples, k of them were at time t0. Now, if you just put them together, the one that you observed at time 0 and the one that you observed after that, you can write down the likelihood function. And then when you write down the likelihood function, of course, there is this mechanistic model that goes here for the mean model for the trajectory. But other than that, everything else looked like just statistical models that you might be familiar with. So this depends, of course, on a set of parameters. We just put them all together. These are some of the parameters of the mechanistic model and the biological variance, technical variance, and the mean trajectory, the mean at time 0. These are collectively the parameters that we want to make inference on. We want to get the posterior distribution of these parameters. So we put some priors on these, and then we get the posterior distribution. To begin with, we actually start with some simulations, so some synthetic data. We actually basically create these trajectories and for MPP, for HSC, and so these would be the true trajectories. So we fix the parameters. So they show the true parameters, so here you can actually see there. So this vertical line shows the actual true parameters. This is the prior that we put on the model parameters, and given the observed data that we simulated here, this is not the real data we simulated here, we get the posterior. And as you can see, posterior for the most part covers the actual true value of the parameter. Not always perfectly, sometimes it's closer in the tail, but for the most part, the model works. So if you fix these parameters, generate some data, give it to the model recovers the true values of those parameters. And we did the same thing for real data. So this is actual real data. So here we don't have those vertical lines. We don't have the true parameters. But we can still see the prior that we put on the parameters and the posterior that we got for different values of the parameters, eta, gamma, sigma. So this basically shows all the parameters. Now, so this is basically the model, and we showed that how it works. But our goal was that now can we use this to design a proper experiment? So to make sure that when we design this experiment, our resources don't go to waste. We actually gain some information. So in a nutshell, like how many of these subjects we want, how many data points we want, and how we should spread out these data points. How can we find the optimal setup. So we basically look at all these parameters, number of days, number of mice, and that would be basically define a set of experimental designs. We call it D. So our goal is to find the best value of D, the best setup for this experiment, given some specific utility metric. So we have to define what is that we are optimizing. So in this case, when we were looking at the real data, as you saw probably, sometimes you have the prior. Maybe actually, I'll get to that. Actually, look, if you look at it here, maybe this just gives some intuition. For some parameters, you define a prior here, and data significantly changes your mind and says, oh, you know, like this is the posterior distribution. So data provides a lot of information, moves you from what you knew before seeing the data to what you know after you saw the data. But then there are some parameters, as you can see here, this is the prior, this is the posterior, so data didn't provide that much information. Basically, before seeing the data, after seeing the data, you didn't change that much. Here's another example. But there are other examples like this that you gained a lot of information. So that's been our goal. We want to just to make sure that we design it in a way that the data provide the maximum amount of information that we need. So we define that by the KL divergence between the prior and posterior. So how much data shifted you from prior to posterior? So we want to maximize that. So that's what we define the Kohlberg-Leibler divergence between the prior and posterior. We define that as a metric, as a utility metric that we want to maximize. This is, we get the expectation of that basically over the distribution of the data. And then we call that U of D for each design D, for each possible design. Look, 3 mice, day 1, 3, and 6. That would give you the one value for this utility. And we can try that for a grid of these values and find the best design based on the one that has the highest amount of utility. So this is basically exactly what I said. So for different designs, so this is like 3 mice at time 0, T1, and maybe day 3, you know, like, so this is one design. So we can generate data, fit the model, get the utility, get the expectation, and then we get the expected utility for this design. But how about I put 4 mice, just time T0 and day 2? That would be another possible design. We can again go through the same thing and then get the utility for this design. And then for all possible design, and then we basically look at the design with the maximum utility and choose that as the optimal design for our experiment. In terms of the computation, I'll talk more about the computation, but we use the Hamiltonian Monte Carlo to basically approximate these utility function. So this is basically getting the posterior sample and plugging in. And there is this annoying marginal likelihood, which could cause a problem. We use something called bridge sampling, which basically is a well-known method to approximate these marginal likelihoods. So that's in terms of the computation. And after we got this, we just basically averaged over the data sets. So this is one example. So we basically looked at the number of mice and then how we want to allocate them over how many days. And we looked at different designs. So we showed 3 specific design, A, B, C. So this is 3 mice a day, day 0 and day 6, that would be design A. It would look like this. As you can see, there's a lot of uncertainty. This is not enough data. And then you go to design B. As you can see, the estimates are a little better. The uncertainty is reduced, but maybe it's too much. And this is design C. So this is it shows the mean utility for these different design. And as you can expect, of course, as you collect more data, you expect that the information increases, but that's not the only thing. How you allocate them, that's also another factor. So just even if you have a lot of mice, but if you don't allocate them properly, that might negatively impact the utility. We could also do, if we are just 2 parameters, for example, say we are only interested in these 2 parameters, we can basically optimize the design with respect to those specific parameters. We say, well, I can, like biological variance, technical variance, I'm not that much interested in those, but the renewal rate, like cell division rate or feedback parameters, these are the ones that I'm interested in. You can basically do the same thing for those and find the optimal designs for those. So this is again, like an example that I showed you before, and just shows the information gain for the 2 parameters that we were interested in. So based on that, we could design so we actually did this. So we have designed the experiment. We kind of delayed because of pandemic, but we are going through with this and collecting more data as a follow-up on experiment. So far I talked about, I started with an illustrative example just to show you big picture what we are trying to do. The mechanistic model tells you the trajectory, the mean model, and then you basically inject some noise, allow for some variances because the observed data is noisy. You want to account for that. And then you are in a familiar territory. You are dealing with a statistical problem. And within a Bayesian framework, you just put a prior on those parameters and get the posterior. And then that would be the basis of your inference. And we use that basically shift from prior to posterior. We define it as a utility of how much information was gained from the data. And we try to maximize that by properly allocating our resources in the experiment. Now, something that so that basically, in terms of the modeling, I'm done. This was the first part, the design part that I mentioned. Now the actual inference, because it's easy to say put the prior and get the posterior. That's easy said and done. But we realize that especially for these mechanistic models, that could be very challenging, and it could create, for some of those we had to wait for a week, to get the results, because we run these MCMC algorithms, and then within each MCMC algorithm, there is no analytical solution for these mechanistic models, for these ODE and PDs. So we have to use numerical method to solve them. So it can become very computationally intensive. So that's why we thought, we want to develop a scalable framework that we can actually use these mechanistic models within the Bayesian framework more efficiently. So this is basically what I presented, the illustrative example and real example. This is like a more generic version of that. So this is called Bayesian inverse problems, because you have some input through some model, you have a forward map from the parameter to observation. And then the inverse problem is just now going and making some inference about those parameters given the data that you observe. And the inference we make is, as I said, through some posterior distribution of the parameter in this case. So a more generic version of the model that I just discussed. So now there is a forward map GeoView. We put some noise around it, and that defines the observed data. You assume some distribution for the noise. And then from that, you can basically get the likelihood function. And the only difference with like the usual statistical models that we have seen, this forward map is basically defines the mean. It comes from some physical or biological laws that they are expressed in terms of ODE and PDE systems. And our goal is to get the posterior distribution given some prior mu naught. We want to get the posterior distribution of mu given y. That's a little more generic framework. But as I said, this implementing this is not that easy because we have to solve this computationally intensive ODE PDE systems. And also you have to get the posterior distribution, which usually tends to be high dimensional. So that could be challenging. The methodology that we have been we started working on is based on a recent approach called Calibration-Emulation Sampling, which was introduced recently. But we basically implemented that using deep learning methods. The original model uses a Gaussian process. We found out that using deep learning methods actually improves the computational efficiency. So the CES, the calibration emulation sampling, is basically allows for approximate Bayesian inference. The calibration part uses some optimization algorithm. Even though it's sampling, it uses optimization-based algorithm, mainly Ensemble common method, and to basically to obtain some parameters using the forward evaluations, and then uses that to basically approximate the forward map. So we can do it at a lower computational cost. And then when we do that, then we go back and do the actual sample. So it has 3 steps. So I'm gonna show you briefly like how they work. So common filter have been used for state space models, but recently there have been some basically implementations of this for basically parameter estimation for mechanistic models. So some variants of that has been used. So specifically in this context for basically solving these inverse problems. So given the data, can I find the parameter values? And the way it works is that you have like these ensemble of particles that you basically generate them from the prior, you evolve them over time. It's like usual like optimization algorithms, and they basically can use to estimate the parameters. So how we evolve these particles is through this equation. So U is the parameter basically. So this is how U evolves over time. It's a little complicated, but my former student, Shiwei Lan, he's a faculty at ASU now, actually created this nice illustration just to show how Ensemble common filter works. So on the left, these are like, as you can see, it started with some random initial points from the prior, each of these points that they're showing, and then shows that how they evolve over time. On the right, for point of comparison, it just shows a random walk Metropolis. So the random walk Metropolis is doing the sampling. It just tries to approximate this distribution. The Ensemble common filter is just an optimization. It just goes to find this optimal point. Now, random walk is not as efficient as this, but it basically gives you this samples from the distribution, whereas this one is basically the trajectory moves towards the optimal point. Let's go back. So this is Ensemble common filter. So there is a modification of this that it basically falls somewhere in between. So it uses the Ensemble common filter, but it's used for sampling, which is called Ensemble Common Sampler, which basically uses this Ensemble Common filter, but instead of just optimizing this, basically getting this optimal point, it actually explores the parameter space and generates samples similar to random walk, but more efficiently. So that was the calibration part, just getting some sample from the parameter space. Now, with the parameter space, you have U and G of U. Basically, you have that forward map. But evaluating that forward map would be very expensive computationally if you want to do it exactly. So after you get some samples from the parameter space, basically different values for U and the corresponding G of U, then instead of actually using that map exactly, we approximate it. So we use that as in those pairs, because if you saw, like the sampler, the Ensemble Common Sampler, it just explores it and collects some U and the corresponding G of U. We can use those pairs as input and output to some basically predictive model, and then approximate that map between U and G of U. In this case, we use a convolutional neural network. We found out it actually works better than Gaussian process that other people have used, or just dense neural networks, deep learning neural networks. We found out it actually works better. But all we did here, just after we collected those points, U and G of U, we just basically put them in a CNN, and we approximated that map between U and G of U. And through that, we basically approximate the likelihood function, because that depends on that G of U. So we call this now GE, basically emulated, it's approximated forward map, and then we get an approximation of the actual likelihood function. So the emulation part allows us to approximate these forward map. And as I said, we actually showed that using CNN compared to a dense neural network or Gaussian process, we can actually do a better job in terms of approximating these maps, these functions. Both the actual function and its gradient, because later on we need both of them. Now, after we collect some points from the parameter space and then approximate the map, now we actually have to use the sampling, like the MCMC sampling. We still have to deal with this high dimensional probability distribution. So to avoid that, the last part we added, we basically mapped this high dimensional posterior distribution to a low dimensional latent space as latent representation using an autoencoder. And we do our sampling in this low dimensional space and then map it back. So what we do when we get these samples, we use an autoencoder to project them into a low dimensional space, do the sampling here, and then project them back to the original space. And this way allows us also to deal with this high dimensional probability distribution. So this is basically what I just said, this is for the sampling part. So basically, if you have a sample, you project it into the latent space in this case, the U that you got, and then you can run your sampling in a low dimensional space, and when you have a proposal, you can project it back through the encoder and decoder part of the autoencoder. Okay, so this is just an illustration of how this works. This is it's a three-dimensional parameter space. Here we just use PCA instead of autoencoder, which is a special case of autoencoder. Found a two-dimensional space. So from the three-dimensional space, mapped to this two-dimensional space, ran the sampler, got a proposal, mapped it back. And as you can see in the three-dimensional space, it is actually exploring the parameter space very well. This is just an illustration. Putting together these three steps, the calibration and emulation, and the emulation with CNN, and the sampling with autoencoder, we call that dimension reduced emulative autoencoder Monte Carlo DREAMC algorithm. And as I just basically said, it runs that Ensemble common sampler to generate samples from the parameter space, use those to approximate the forward map, and then use that map instead of the actual likelihood evaluation of likelihood function. We use this approximate likelihood function, and then run the sampler, but not in the original parameter space, in the reduced parameter space, low dimensional parameter space, and that's the sampling part. So that's basically how it works. So this is just a simple example, just showing that the actual, this is a Hamiltonian Monte Carlo sampler. This is the ground truth for us. This is how it works. This is if you just use the emulator, not the dimensionality reduction part of it. And this is if we use the whole thing with dimensional. As you can see, it does a good job. It approximates the posterior distribution very well. For a more complex distribution, the emulated part still works, but the dimensionality reduction, because it's not always perfect. There are sometimes the information is lost. So you get the distribution somehow to some extent, but occasionally, as you can see here, it's not perfect, but it's an approximation, and it's much faster. So it's a trade-off between accuracy and computational cost. And this is just a real example, is the elliptic PDE problem, and different algorithms, and these are basically our algorithms. As you can see, it can improve the computational cost, the computational efficiency to 3 orders of magnitude in terms of this speed. So it's my last slide, 10:49, so I think we are right on time. So in summary, there's this growing interest in uncertainty quantification. People have been using mechanistic models. There's more interest now to actually account for noise and uncertainty in these models. So, and this is what created a lot of enthusiasm in applied math and its application in physical sciences, biological sciences, and engineering. Embedding mechanistic model in a Bayesian framework provides a natural approach for uncertainty quantification. It just as you saw, is just conceptually is very simple. Now implementation could be difficult. We actually showed that how this works for a specific biological problem that we have been working on. But as I said, computationally, this could be challenging. And that's what we use deep learning in conjunction with this approach, calibration, emulation, and sampling, to show that how we can also improve the computation. These are my collaborators, Vladimir Minning and John Lowengrove from UCI, and these are our collaborators from the School of Medicine that we got the data. And this is my former student, faculty at ASU now. We did the computational part together. and my former student, Luis Martinez Lomelli, who have that GitHub tutorial and also basically developed the model and implemented it. And we were supported by NSF Simon's Center for Multiscale Sulfate Research, NSF, and Simon's Foundation and NIH. Thank you.
Oh, thank you so much. That was very interesting. So many techniques coming together to make this work possible. Does anybody have any questions for Babak? It looks like we got one right away from Katie in the chat. Katie asks, "Are you able to account for emulator uncertainty when you use the CNN instead of GP?"
Yes, I mean, even GP is not perfect. It's still an emulator, you know, like it's still like an approximation, if I understood the question right. The CNN, I mean, like the emulator is not perfect. And at the end of the day, you know that you're not getting the exact posterior distribution, you get the approximate posterior distribution, and you can try to see that how much information is lost and the approximation. But CNN versus GP, both of them are emulators. They approximate the forward map. So both of them in the same category, except that GP, if you see the papers, we actually talk about this, that GP have some limitations that CNN doesn't have. I don't know if I answered the question, but in terms of the approximation, both of them are approximate. And you are right. You can keep track of like how much its approximation costs you in terms of accuracy and how much it provides computational efficiency. I don't know if I answered the question.
Any follow-up question, Katie?
I guess I'll just unmute and ask. My main question was about with the GP, how you actually have a measurement of that prediction uncertainty. So that kind of gives you some idea of how you can keep track of like how far you off you're off. Is there something you can do with a CNN instead? Because
yes. No, you are right. You are right. There is that aspect of it. You're absolutely right. You lose that with CNN. Absolutely. Sorry, I misunderstood your question first.
Oh, no worries.
You're absolutely.
Yes. It's a really hot topic right now, so I was interested if you had any input on it, but thanks.
Yes, no, you're absolutely right. In this case, we just wanted some, for us, that wasn't as important as it could be, like in other contexts. We just wanted, like a fast, like a quick approximation of the forward map so we can run the MCMC. But you are right, there is that aspect of GP that CNN doesn't provide. You're absolutely right. It wasn't as crucial as what we were doing here.
Yeah, I'll take a look at your paper and see how they compare.
Yes.
Thanks.
Yes.
Any other questions for Babak? I'll ask one. I'm wondering when you were talking about the utility metric that you use to evaluate the quality of the various proposed designs, how can you compute the utility in advance of having the data that that the experiment that is proposed would produce? Could you walk us through that a little bit more? I got a little bit lost in the details.
Sorry, no, that part of it is simulation. Yes, sorry, yes, we don't have the data yet. We actually have a pilot study to basically fine tune our model, and like based on some preliminary data, we did use the preliminary data just to fine tune our model, just to make sure that the mechanistic model makes sense, explains the data properly. But after that, because you are thinking about all scenarios that you don't have the data, given those scenarios, we simulate the data and then estimate the utility. I think that's what you were asking.
Yeah, I think that was the key step that I was missing,
Yes,
the
yes.
simulation part of it.
Yes, I went a little quickly. Yes, that part is all simulation. After you fix the model, you say, okay, this is a model based on the preliminary data. It seems that it explains the system well. Then after that, getting the utility function and estimating it is based on just simulation. So you fix these parameters, simulate the data, and then estimate the utility for that setup, and then you get one value, and then for each design. Yeah,
Okay.
that part is all simulation, not real data. You are right. Yeah.
Okay, thanks for that additional explanation. We've got a few more minutes. We can take one more question if it's out there.
So I usually avoid like having two different topics in one talk, but this one I thought it was related. So the first part was more about the modeling, and the second part is more about computation inference. They go hand in hand. You can't separate them. But the drawback is that then there will be like information overload because you try to cover too much in one talk.
Oh, I think it was very interesting to see the whole workflow there, and I think that was a good choice. I enjoyed seeing that.
Thank you. Thank you so much.
All right. Well, if there's no other questions, I guess we'll end here. Thank you a lot, Babak, for coming today and talking to us and taking time out of your schedule. If you'd like to have further conversation with Babak, I'm sure he'd welcome your email. So please reach out. And also, I will make sure that Mike follows up with you for a further discussion about collaboration with UCI and LLNL DSI.
Definitely. I look forward to it. Thank you so much. Thanks, everyone.